Welcome. Today we are going to learn about the fundamentals of equilibrium vapor-liquid separation. So in this today's lecture we shall be looking into the following topics. First is the condensation evaporation in pure and mixture of components, about relative volatility, then flash vaporization and partial condensation, which are the basis of any kind of vapor liquid separation processes, then flash analysis, and we shall see that what is the cascade of flash units. So first let us look into the condensation and evaporation characteristics in pure and mixture of components. Here we shall see that for pure component and the mixture of components, the behaviors are different. Now at a constant pressure, for a pure component, evaporation or condensation takes place at constant temperature, while for a mixture it takes place over a range of temperatures that are bounded by the dew point and the bubble point temperatures, as we learnt earlier. Similarly, for a given temperature, for a pure component, the phase change occurs at a constant pressure, while for a mixture of component, it happens over a range of pressures bounded by the dew point and the bubble point pressures. Next we come to a parameter which is important for the analysis of the vapor liquid separation systems. Now this is relative volatility. To understand this, first let us see what is volatility. Volatility, as we know, that it is a tendency of a liquid component to go to the vapor phase. So it is defined like this, that it is the for a given component I at equilibrium, it is under vapor liquid equilibrium. We write like this, that Ki is the equilibrium constant, is defined as the ratio of the mole fraction of the ith component in the vapor phase to the mole fraction of the ith component in the liquid phase. So this is the equilibrium constant or the volatility. The more the value of Ki, the more the tendency of the component to go to the vapor phase. Now relative volatility compares the volatilities of two components. We define it with respect to two components, like relative volatility of component I with respect to component j, and is given by alpha ij, is defined like the ratio of the Ki to Kj. Now if we see that if the relative volatility is equal to 1, that is Ki is equal to Kj, that means the two components will have the same tendency to go to the vapor phase. Then we will not be getting any kind of separation. So what we want for separation is that the relative volatility should be as away from unity as possible. If it is equal to or near unity, then it becomes very difficult or sometimes impossible to separate the components by these flash or the condensation methods. Then we have to adopt some other means of separation. Now this relative volatility decreases with an increase in the pressure, but when a system follows Raoult's law, that is ideal liquid and ideal vapor, in that case relative volatility is independent of the pressure. For a binary mixture, the relative volatility is defined like this, that for a component with Y as the vapor phase mole fraction, X as the liquid phase mole fraction, that means for the other component 1 minus Y will be the vapor phase composition and 1 minus X will be the liquid phase composition. In that respect, we find that we are able to define the relative volatility for a binary mixture, like in terms of only Y and X. Now this particular thing may be used to generate the vapor liquid equilibrium curve, which we saw in our earlier lecture for different temperatures and pressures. Now here we come to the flash vaporization and the partial condensation, which are used for separation. Now flash vaporization is the rapid vaporization of some liquid which is saturated by either lowering its pressure or by increasing its temperature. On the other hand, partial condensation means that we are cooling the vapor mixture and then partially condensing it to get a liquid phase. Now, when we are doing so, what happens that in the flash vaporization, the vapor gets enriched with the more volatile component, leaving behind the less volatile component more in the liquid phase. On the other hand, for the partial condensation, the less volatile components more go into the liquid phase, leaving behind the more volatile component in the vapor phase, and that is how we are able to get separation. This flash vaporization is used for separating volatile components from a liquid, while for the partial condensation we use it to separate the less volatile component from a vapor. And both these separations are more effective for widely varying boiling points, because the boiling points, if they come closer, that means the relative volatility comes closer to 1, and these components will be difficult to separate by vapor liquid system. Now, let us see how we describe the process both for the partial condensation and flash vaporization. The feed is either partially vaporized or condensed. Now, subcooled liquid feed, if we have, then it has to be first brought to the saturated condition, then only we do the flash vaporization. And if we have superheated vapor, first it has to be cooled to make it saturated, and then we do the partial condensation. In both the cases, there will be generation of some vapor or some liquid, and the extent of the vaporization of the feed or the extent of the condensation of the feed, these are given by some ratio V by F, that is the vapor to feed ratio, or L by F, the liquid to feed ratio, that depend on the amount of heat added or removed from the system. Now, feed temperature and pressure do not affect these conditions. They are more dependent on the equilibrium temperature and pressure of the product vapor and liquid streams. Now, here the pictorial depiction of these two processes. Here we find for the partial flash vaporization, we have a liquid feed with these conditions, that F represents the flow rate, ZF is the feed composition, P in, T in, H in, they are the pressure, temperature and the enthalpy, and these are passed through the heater. It is brought to some higher temperature, and there is a valve. This valve ensures that we are able to decrease the pressure or throttle it, and when we do it, this liquid flashes, that is goes into a vapor phase partially, and then this is a flash drum in which we are separating out the two phases, and we assume that these vapor and liquid streams are getting sufficient time for exchange of the various components and come to equilibrium, and ultimately we get the vapor product from the top and liquid from the bottom, and if need be we may have to add or take out some amount of the heat of this flash. This depends on whether we are doing isothermally or whether we are doing adiabatically. Similarly, for the partial condensation, we have a vapor feed. This is passed through a cooler, and by passing through cooler, again we generate the two streams, that liquid is generated from the vapor, and again this particular phase separator gives us a vapor and liquid stream, and it could be carried out either isothermally or adiabatically. If it is adiabatic, in both the Q's will be 0. Now, let us go to the analysis of these two processes. Whatever we are going to learn now is applicable both to flash vaporization as well as to partial condensation. Here we are assuming that there is equilibrium after separation, because equilibrium will tell us about the maximum possible separation. So, that means the vapor and liquid streams are coming to equilibrium. Now, this analysis is based on the following. First, we do a degrees of freedom analysis, in which we find out the minimum number of properties to be specified to completely describe the system. And next we come to a set of equations, what we in short call mesh. This mesh stands for, M stands for mass balance, E stands for equilibrium relationship, S stands for summation equation and H stands for the enthalpy balance equation. Now we come to the degrees of freedom analysis or DOF analysis. In this, before we go to do that, we first see that each stream is identified by temperature, pressure, flow rate and its composition, and composition means we are assuming that there are C number of components in any stream. Now, here we are going to refer to this particular system. Here we have a feed which with flow rate of F, and we have vapor and liquid which flow rate V and L as the product, and then we have used some few notations. Here the notations are that by Z I represent the feed composition of the ith component, Tf, Pf are the temperature and pressure of the feed respectively, the Hf is the specific enthalpy of the feed, Yi is the composition of the vapor product, Tv, Pv are the vapor temperature pressure respectively, Hv is the enthalpy of the vapor, Xi is the composition of the liquid, TL, PL, HL are the temperature pressure enthalpy of the liquid stream respectively, and Q is any kind of condenser or evaporator duty. Now we first understand that how to count the variables. Now here we have C number of components in each of the feed, vapor and liquid. So Zi represents basically a vector of the compositions. So we have put this curly bracket, and here we see that there are C number of components. So C number of mole fractions. Similarly, we have Xi, we have C number for the liquid. For the vapor again we have C number of components, that means C number of mole fractions. Then the flow rate of the feed represents only one variable. The Tf, Pf, V, Tv, Pv, L, TL, PL, Q, all of them represent only one quantity. So we find that for all of them we count only one variables. Now we see the total number of variables are 3C plus 10. Now let us see that how many equations are there which correlate these variables. First we come to the overall mass balance, that is F equal to V plus L, that is only one equation. Then we write the component material balances for each of the species. Then here we find for ith species we are writing that whatever is going with the system, this is is and coming out is Lxi into Vyi. These are the component flow rates. So here we have C number of equations. Then we have thermal equilibrium, TL equal to Tv, that represents 1. Then mechanical equilibrium, Pv equal to PL, that is 1. Then chemical equilibrium, Yi equal to Ki Xi, and it goes for each of the components. So we have C number of equilibrium relationships. Then we have summation equation which tells us that the summation of the mole fractions always equal to 1. So we have 3 equations for the 3 streams, and that is 3 number of equations here. And for enthalpy balance we write it for the overall system. So here we have only one equation, and then in this equation we have the enthalpy going with the feed and some amount of Q. This Q may be positive or negative depending on whether we are heating it or cooling it, and then we have the enthalpies going out with the liquid and vapor streams. So this is 1, and then we count these equations. This comes to 2C plus 7. Now please understand that in these equations we have many variables like this Ki, then Hi, Hf, Hl, Hv. All these things have to be found out by the knowledge of temperature, pressure and the compositions. So we are not counting them as the number of the variables. So now we have the degrees of freedom F as equal to total number of variables minus the number of equations correlating these variables, and this comes out to C plus 3. That means we have to specify C plus 3 number of properties to completely describe the system and analyze it. Now we write the flash equations as I told you that this referring to this particular figure, we write the overall material balance as F is equal to L plus V. Then we have the component material balance as molar flow rate into the mole fraction, that is the component molar flow rate equal to the Lxi plus Vyi, and then we have the equilibrium relationship, that is Yi equal to Ki Xi, enthalpy balance as this, and then we have the, after writing these equations, what we do, we simply combine the various equations. So here we are combining the overall material balance, the component material balance and the equilibrium relationship. By combining this, we get this equation, and in this equation we have taken out the L by replacing it by F minus V, and also taken out Yi by replacing it with Ki into Xi. Now when we rearrange this equation, we get this particular equation, and in this particular equation we find the mole fraction of any component I in the liquid phase is given in terms of the mole fraction in the feed and this V by F ratio, that is the how much fraction of the feed has been vaporized, and in terms of the Ki. Similarly, when we combine the overall mass balance with the enthalpy balance, we get this particular equation for this V by F. That means this V by F is given in terms of the enthalpies. Now we have the Yi equal to Ki Xi, that is, we multiply simply this equation with Ki, we get the value of Yi. Now we are going to use a summation equation, that summation of Xi is equal to 1, summation of Yi is also equal to 1. So when we subtract this summation of Xi and summation of Yi, we get 0. So that is how we are able to get this particular equation. In this equation can be solved if we know the value of the V by F and the value of the Ki. So here we define this equation in terms of some factor psi, which is nothing but the V by F, and here we have put this thing in terms of psi and Ki. So this is a non-linear equation, so we need to use some kind of numerical technique to solve these equations. Please mind, this equation stands for all the I components, and this, once we know the psi, temperature, pressure, we can determine Xi and Yi. Now let us go to solution of these equations. Before we go to solve it, we have to first make sure that we have a partially condensed vapor or a partially vaporized liquid, because if it is pure liquid or pure vapor, then we are not going to get any kind of separation. So to know this, again we have some kind of rules, that first we shall see that if there is a partial condensed or partially vaporized, then psi I must be lying between 0 and 1. So here we have that if all the K values are more than 1, that means we have superheated vapor, so we will not be solving it. Again, if we find that all the K values are less than 1, then we have subcooled liquid, then also we will not be performing any kind of separation analysis. Now if we have some K less than 1 and some K more than 1, then what we need to do? We shall be putting psi equal to 0 and check whether we are getting R psi more than 1 or 0 or not. If it is more than 0, then we have a mixture which is below its bubble point, that it is subcooled. And if we put psi equal to 1 and we find that R psi is coming less than 0, then it below it's above its dew point, that means it is a superheated vapor. Now another way of doing checking that whether we have a partially vaporized liquid or partially condensed vapor or not, what we do, we take this summation Ki Xi and this summation of Yi by Ki, and we check their values, and we find that various combinations have been given. By looking at these various combinations, we can make out that whether we have subcooled liquid, saturated liquid, mixture of liquid vapor, saturated vapor or superheated vapor, and naturally for our separation we would like to have mixture of vapor and liquid. Now once we have made sure that we have a partially condensed vapor or partially vaporized liquid, now we go for the solution, and here we use a Newton's method, and we know that psi has to lie between 0 and 1, and by Newton's method we know that this is a recurring relationship we find for finding the root in Newton's method or Newton-Raphson method for multiple variables. We find that psi, this Ki represents, this K, small k represents the number of iterations. So we update the psi value from the previous value of the psi by this relationship. This is R psi k, and this is r prime, that is dr by d psi, this derivative. So with this particular relationship we can update the value of psi, and this is the expression for I prime psi k. And what we do that after each iteration we may check that how the value of psi between two consecutive iterations are changing, and there are many ways of finding this, doing this comparison. One way is this way, that we take the absolute value of the difference between the psi's in two consecutive iterations, divide it by the psi value of the present iteration, and check whether it is coming less than some user defined convergence factor. Now if it is less than that or equal to, then we can say that we are converging to the solution, otherwise we have to keep repeating this exercise. Now after doing this flash analysis, we also find that this analysis may also be used to find out the dew point and bubble point calculations. For the bubble point calculation, we find that there is no vapor, and so there is bubble point means what? As you recall, the bubble point means when first time the liquid is going to produce the first bubble. So in that situation we have only the liquid present with us and there is no vapor. So that is why the vapor has been taken to be 0, and if I put, that means the feed is equal to the L, so we find that psi is equal to 0, and if you put psi equal to 0 in the previous equation, we find we will end up with this particular equation, which is same as the one we learnt earlier in the lecture on dew point and bubble point calculations. Similarly, if we want to find the dew point, then what we do? We simply take the L to be 0, because dew point means a vapor is going to condense and give the first droplet of liquid. So in that case we still are going to have the liquid is not present, so we put L equal to 0, and then feed is same as the vapor, and then that means psi equal to 1, and when we put psi equal to 1, we find that this is the equation we get, and this you see is the same equation we had earlier for the dew point calculation. That means this particular formulation of flash is not only going to give us the solution for the liquid and vapor streams we obtain after flash vaporization or partial condensation, but they may also be used to find out the dew point and bubble point pressure or temperature. Now this particular flash is useful for separation, but we find that the vapor and liquid streams may not meet the desired purification or desired separation. So to make the desired separation, what we need to do, that we need to make them multiple flashes may be carried out. So by doing multiple flashes we can achieve the desired separation. So here we have shown a typical thing, that here if we want to enrich the vapor, then what we do, that we take the feed here, and then after first flash we take this vapor out, and this vapor is again going for partial condensation, and it is again in the second, after the second element, then again we take the vapor out and go for another partial condensation, and in this way by consecutive partial condensation we are able to enrich the vapor. That means we are making the vapor more and more enriched with the more volatile component. So here we are not doing anything with the liquid, because our desired product is the vapor. On the other hand, if we want to have a enriched liquid, then what we do, we take this feed and we again flash it. Now we are dealing with only liquid. This liquid is taken for flash vaporization consecutively until and unless we get the desired separation in the liquid. So when we combine these two things, then we find that we can get both enriched vapor as well as enriched liquid. So that is how we are doing the cascade of flash units to get the separation of a components, and this is true not only for just binary components, this may be used for multi components also. Now these are the references which you may refer to for more detailed studies on these processes. Thank you.